I would like to welcome you to the workshop today. It's four main talks. The first two, the morning one, are more technical one, in a sense that we are going to talk about time series and how we can analyze them. And then afterwards, we're going to see a few things about image processing and altogether, specifically for the project, meaning that we're going to see some examples for rare earth materials. So I will start the presentation, the first presentation, together with Stelina. I will just show you a few things about time series pre-processing, and then live coding through Collab. I hope that it will not collapse, so bear with us. Let me start. So as you see from the title, it's all about data, and specifically for data and pre-processing, raw material supply chain. So what's the final goal of this thing is, of course, monitoring and forecasting to see with this magic ball things that can happen. Some wars over happen in the Iran side and Ukraine, but from our side at least, logistically we'll try to, and we hope that you will be with us how you can process this data. Okay, a second. Nice. So as to the outline, we have some questions. What do we mean with data pre-processing and why this is important? I think we even sorry about this, in specifically in material supply chain data, some general workflow for standardization, imputator techniques, and so on and so forth, cleaning and validation, of course, some canonicalization and double counting, as we said. Then some basic principles. We have spaces within the data, right? So we have a time points, and then some what we can do there. How we can use one neural net driven imputation techniques. Then later on, we have to check what we call the mass balance, and from there we then to extract some properties of the signal, some features of the signal. Why? Because then we will facilitate a little bit the forecasting. And then at the end, we just have the data ready with the forecasting. So I'm not sure, are we going to show forecasting? No. So this is only about pre-processing today, ready for. So we need, why? Because you can imagine that this is a kind of a bridge that connects the heterogeneous data, the data that comes with different units, and you have to think in terms of multiple sources, so data that come from different sources, so we somehow have to control them. Then, you know, imagine that we have a pineapple. So we now, you know how there is the pineapple with the leaf, with the outer cover, and now we start cutting all the outer side. What is the goal with the pineapple? Is to eat the pineapple, not as it is. We need the inside pineapple, right? So more similar. So we start from the outside of the pineapple. In our case, it's the heterogeneous observations with already data. So do not misunderstand here. We are going to extract data from somewhere and then to make data here. And then you see here the word trust. So we need to trust what we develop, the modules actually that we are going to and let's say do the forecasting, right? So we start from the raw data, as we say here, different sources, different units, missing entries for the whatever reason that can be, and reports that come from companies, that comes from institute, that comes from Europe, that comes from the whatever source that we have in our hands and is available. And imagine that they describe the same thing, but in a different way, or sometimes in the same way, and we have some overlap. So there we need to be able to understand that this time series that they describe here, it's the same thing. So we start with this situation with the first step. We continue with cleaning, validation, mechanicalization, imputation, and feature. All the steps one by one with thing. And then, of course, I told you we are going to remove the shapes out of the pineapple and then to have our slice ready to eat them, right? So clear variables and ML models. Okay, so far so good. So first of all, we need to understand, as I said, what are the records underneath, right? And whether we can compare it, can combine it, and then we can use it in a model. So specifically, in the domain that we talk about today, we have to talk about sources from different, let's say, reports in general or general different sources, and that can be mining, for example, refining, trade, kind of capacity, demand data sets, and this is the difference inside. Why? Because we have different organizations, different companies, right? So we need first of all to understand these things, and then since we have put all of this data, for example, in an Excel sheet or something else, then we start understanding the data. So one unit might be kilos, the other one can be tons, the other one can be, I don't know, whatever. Monetary values, as we say here, percentages, quotas, different units in general, right? And then, of course, we have to understand also the different graduality that we said over there. So we might have some country-driven statistics, some company record, site-level observations. So again, just to take examples, different situations that we need to handle over there. We don't know sometimes because the company report to something and we don't know if this is a final or something else. There is a kind of uncertainty there. We don't really know what we look for. So we have to separate this, take intermediate forms. See, for example, that, okay, now we have, let's say, procurement from a transit node, so it's going to go somewhere else, or is it the final, for example? What else? Downstream categories and the broad labels there, is to our experience, may include specific products. So we need to go into more details to understand. Other things that we have to be aware of. Yeah, for example, we start checking a report or we start extracting data from there. And as I said at the very beginning, some years are missing there. So what we have to do, for example, we're going to sit around. There is, for example, a whatever action that started in 2020. And for a reason, after 3 years, so we have other news from that specific project or action. So we have this discontinuity of the project. We also might have a sparse tree or product set. See what we'll do there. We need to start modeling our gaps that we have there, right? To see what we can do later on. And we cannot neglect the last one, which is about noise. Again, another thing. Meaning here, one thing can be duplicated. So one times. Some parent aggregate can be there, inconsistent labels, and to compare with oneself, what shall I do now with this label? Shall I for that one? And then you, let's say, acceptance up to the, and then of course, the risk here that we double if the rows are summed to something totally different. Okay, and okay, let's now start basic pipeline. Imagine you can just keep a screenshot of this thing or whatever else. This is a very typical pipeline, not something new, something that we this is a very, I would say, in our case, we work many years, and we start, as we said, with the raw data. So, for example, we have files and databases, or Excel files, or CSV files, or XML, whatever you like. And we continue, as I said before, with clean plus validation. This data manually is fine, and continue with this thing. And then can come and compare signals that we start extracting from this raw data. Analytical, let's say, level that we have there. So how to say this? Imagine that we have a bit blur and start cutting the picture into pieces. But and to have the clear picture, so we need to do a very fine reconstruction of the image at the very beginning. Imputation is there to say that we have many gaps, and this is why, because as I told you in the very beginning, we want to facilitate a little bit the forecast, meaning that I have many options here for the forecasting models. I can either give clean or reduced noise data sets, the time series, or, and in this case, I need a lot of this time series, and then that the model, the later model, will be able to understand from the different behavior of the time series. Or what else can I do? I can extract information now, which is hidden signal, which is a time mean value, deviation, kurtosis, whatever else can be there. Spectral features, power, specific bands, some that we used to have there. We can also play with the time, meaning that we can come and quantize the time and from the time space symbol space, to start talking about complexity, to start talking about uncertainty and other, let's say, stochastic features, if you like, here. So we have several directions. So at the end, you can as a table, and then vectorized driven. So in vectors, you can have those features. You can continue with the ML ready dataset that we say here. So we stop there, and then we are going to show a few things about this. So in the design principle that we want to separate the steps that define the main signal from the features. This is one thing. Just to say here, nobody will guarantee you that all these steps that you do this, you do that, you do this and that will be fine. Always you need to check. Because remember the example with a pineapple. You might close your eyes and start cutting it, but you don't know at the end if it is okay or not. Okay. Cleaning. Okay, I might keep it like this. Is this better? Because I might do some moves and then, yes, okay, then they lose me. Give me a second. Okay, let me continue then. So we start with the first one, which is a cleaning and validation, meaning that validation here, as we say, is not only a data quality check. So here, I also had the whole, if everything is fine. So here we need to define how each record should be used for a last step there, which is the ML ready process. So visually, and I'm not saying that I will go time point by time point, but through some visualization, some empirical distance there to check that the data is fine. What we can do here actually is to see that, for example, First criterion, completeness. Do I have any missing cells, any empty streams, some sparse period, something else inconsistent and distort my continuity there of the data? Because imagine that we have the time and the signal should be continuous with anomaly, with whatever else. The next test in terms of units, country names, product labels, and other stuff that can be here. Other thing, so to see if I have there a -2 tones, is this correct? No, something there during the numeric text. So we have to check also such a things or some other important conversions, which at the end of the day will end up not available, not exist, none, or where else can be there. Duplication, I think that I convinced for this. Temporal behaviors, so some discontinued operations or these subtract sums that we might have in the data. And then, of course, the noise, the artifacts, the reporting artifacts, the aggregate rows and the mix rows that we might have. That we have to do there for the data. Cleaning procedure. Cleaning procedure contains such steps. Standardize as to the country, as to the company, as to the product and data type levels that we might have here. Sorry, remember at the end of the day we need unitless data to continue with the forecasting. So we continue then here with the harmonization version of the data to make them with comparable units, and even in the best scenario to remove all units from our data. And of course we have there and remove all these physical quantities that we have there. So in fact here we just go from the one space of the data to a unitless data space. And believe me, there are several methods here to use to do this step. Keep our target. So to have a reliable physical production or output signal here. So here again, I will say let's go one step back and be sure through the validation that the time series looks fine. To see if I already have some features from the raw data that we extracted, and then to keep them because I'm going to use them later on, or the features that I'm going to extract. And then some flags that I might have there based on what? Based on the imputation that I will do, because also imputation is not a miracle, right? So it has also some flags, and flags tell me trust this new time point that I extract for you with this confidence, or do not trust it. A very standard step, which is the outlier detection. We have a time series that goes, and then we have something crazy going up, right? Some statistical procedures and machine learning procedures where we can go and detect those outliers. Again, we have to be careful because this outlier might be a real value and not only a noise. So even there, we need a compromise with ourselves. So I want to say with this is not trust all these methods with blind eyes, right? So for record, receives a model in a row. So we have here target, feature, metadata, and of course the flag, as we said here. Now to the other step. I may talk too much, so let me go a bit back. So we start with this blob, and now we go with the canonicalization, and then we'll continue with the rest. So to this step now, as we said, we want to canonicalize our data, and of course to avoid double counting. So before any kind of aggregation, we need to define what one final represent and how now the overall records should be handled. Just to the definitions here, just to define this kind of difficult word definition. So what we think over here, we come and convert now the data, let's say here, the raw records better, the raw records that comes, let's say, from a different nature, right? So heterogeneous data, raw records, into a consistent analytical representation. For us, what we know, the discrete signal. So this bunch of time points that we will use later on for analysis. So why this matters? Because we want to have the comparison between different time series, right? We want to reduce double counting, and of course, we want to have one signal per target level, and we need, of course, a little bit our source information. Now, if we start unrolling here all the situation, and then the techniques, we can talk about able normalization, unit harmonization, entity resolution. This is another chapter, I will say. We're going to see a few things later on. And then let's say a hierarchy-aware record. Then we continue. We can have some criterion or rule-based deduplication there, how we can merge, in fact, over there the duplicates, to be able to control the aggregation, to give some priority to our sources, which will come first, because not everything that we extract, we don't know, we will see at the end. And then, of course, to provenance here, the tracking. Nice. So here we can show just a simple decision logic for or record. So we are going to show you a set of rule criteria that we can follow here. So we have discrete steps. So first of all, we need to come and define the target grain, the entity here, the country here, and stuff like this. And then we can also then we can come and identify the overlaps, meaning the records that they may describe, as I told you before, same activity. Of course, then at the third step, there are over here, source reliability here, and then start creating the actual signal, the canonical, as we say. So this will be then, after all the three steps, the single value used as now the main target that we will use for the later on features. And then, of course, we can retain this procedure for the rest. So we might have some metadata, some over there indicator, and then some risk flag. Again, here to avoid counting, let's say, by sealing layers before the aggregation. Now, since now we start from the raw signals, we check a little bit the data, we convert, canonicalize the data and bring the signal into the foreground, then we continue with what we call missing data handling. So here, as obviously the word said, we have some missing raw records, pre-processed bit, so data, in fact, and we start with imputation. Simply a technique and gives you a recommendation for the missing data that is here. There are, believe me, several either traditional or new methods that you can use. The idea is this one. So I have this bunch of data, this bunch of tabularized data. So in fact, here we have a matrix, and I have some missing here, here, and there. And then with this magic in between, I can then fill those gaps with data. For example, that can be by taking the mean value of these two. An example, the median, whatever else. Here we are going to show you that we recently published, and we are going to show you later on. So to the rules now that we have to follow. So never override here observed values. Of course, do not treat missing as 0 automatically. Why? Because 0 might be a value over here that we have to use. You have to stop all the time the imputation, the train, I think, imputation, most of the times, and the uncertainty. Why? Because remember, in the validation step, we need to check all the time the uncertainty value. To have the separate the observed impute and the low confidence value, keep them somewhere with them. We might consider them as a garbage, and then we just give them up. This is a repetitive procedure, right? So this is why I said that we can have here many methods, and you see that we have like a bunch of traditional, I would say, machine learning, pattern recognition, whatever you like. So we start with a very standard one, mean and median. So simply we just take the neighbors, check the neighbors there, and then we get the mean value or the median, depending on the data set. Depending, if you like, on the distribution of the data. If it is linear or non-linear, one thing. Another, most frequent here that you see in the data set, or I can say that I will fill my values with ones, with zeros, with none, right? Then we have to, we can also have forward or backward fill, meaning that we work with temporal gaps, stable time series. Well, in stable meaning here that the statistical or time series remain, they do not change over time. So we can take before and after, and then we can come and fill from data from that too. And then this one, first of all, the interpolation, some specific techniques that come and fit specific, let's say, functions into my data, and they use the neighbor observations to do this. One example is the SP lines here that you can use in order to come interpolate your data. And then the last two, which is pure machine learning method, the K nearest neighbor imputation method, where it starts with a specific centroid, and then it checks all the neighbors, and through tools like mean or Euclidean distance or Hamming distance or correlation distance. So in fact, underneath there is a criterion that checks the distance between the neighbors over there, and then you come and give the specific values based on n. And then I would say here one of the most famous, I would say, or the most standard, which is the mice, which is an iterative procedure, where here we have model, come and model each variable using again neighbor values in repeated rounds. And if you like, here we can also inherit properties from all the others methods here. Very standard, and all of these for you, do not skip them. This will be your first step. Your first step over here towards robust and stable imputation method later on. So this is what we say. You can consider them as a useful baseline, but they rely only on local time patterns or tabular similarities. So for example, they cannot check the causal effects between different and multiple sources. So you might have different signals. This method here, we just check only one time series, but you might have sources that they share common, let's say, effects, causal effects. In the sense that we can later on, we can use graph theory, for example, and check the property and how these nodes share properties or who gives a flow to another, so stuff like this. So these methods, they can be just straightforward to specific time series. Nice. So the first decision here for the missing data handling is to whenever this gap means missing information or if this is true activity. True zero, what we say here, the activity did not happen. So we over there. In the actual now missing observation, the activity may exist, but it was not reported. So it was an actual value. And then for the whatever reason, let's say broken sensor, who just passed the numbers, forgot to pass this number. So over here, we come and say, here we have a value. see what happened there. And then, of course, we have the future and the planned value, which is not a historical, but we can keep this separate from the text as an actual. As we saw before, and now having all these first the computers, as we saw before, can come here, fill the gaps, but they may miss the structure dependencies. Dependencies, the causal effects that I told you before. Now we have to come and choose how we'll handle these things that we saw before. So we have the observed value exists, so we need to preserve this. We have a short internal gap, so we have to interpolate very carefully. And why to interpolate very carefully? Because if one goes and try interpolation, you will see that you have another bunch of methods. So as an engineer, you have to be able to test them and to see which is the best for you at the end of the day, based again on the data, on the input data that you have. To see here the sparse and the structural missing that you have, how you can handle. So there you can use what we call relation impute with graphs. Why? Because you have different nodes. So we now start treating the time series and nodes, and then we have the so-called relation impute. And then, of course, we can have the future planned values, which is this is keep it separately from the training. We will let's say store the imputed values with some flags, because we want to see later on the method or the guy that came and suggests this value that you just suggest me. Good. If you are also, these methods are very good for you to solve problems and the challenges, because imagine here, and do not forget that we talk about real data, right? So as we say here, specifically in critical raw material supply chain, we often require relational information, which is a simple interpolation cannot solve this problem. So classical methods work best when time series are dense and regular. You have neighbors with observations so that you can use them. And the missing values are local, and then records are mostly independent. Now, in our actual real world, in the CRM data, they often look different, meaning we have sparse annual observation. You have structural mixedness here. Of course, you have heterogeneous reporting and records connected across entities. A difficult situation, not something simple like the simulated data, if you like. So, first of all, as engineers, to understand to the relationship record. So, we have the country in around. So that company can be in many countries, if you like. So that we start with exists this company, and then we have that product and that material and that specific year and that specific month and that specific day and that specific minute, I would say. So depending on the resolution that you have, right? Nice. So for example, here I will just jump into something very novel, something that we look the data now as a graph. The graph, as you see here, is nothing else than a bunch of nodes and relations with them. Graphs are everywhere. Right. So here, the edge that we say preserve an information between me and Stelina, for example, that we are here, or between two different companies, as we said before, countries, whatever, or sources within one company, if you like. In general, this is a relation between the two nodes. And now this representation helps us to model relationships that flat table and does not show something directly. So this representation is an abstract representation and comes and cover all the other data structures that you might have there. And this is nice now. And then we now come and combine it with graph neural models. So with one word, artificial intelligence, inside machine learning, deep neural networks. Deep neural networks, you have hidden layers where those layers do some magic. And that magic can be a sigmoid function, for example, which, or even simpler, will do some convolutions, some multiplications, if you like. And then the model by itself will extract some features. We'll see to some unlinearities that we cannot see with typical methods. And here we make even more complicated by including graphs inside. So instead of very typical convolutions or multiplications that we might have inside, we bring graphs into the foreground. Why? Because we want this graph structure. Why? Because of the data. The data, as we saw before, it is a bit not the very best. So also here, another merit is that we learn from different relationship types. So imagine here, this is a different type of specific data that we have. And then, for example, this is missing. Oh, this is missing. Then I can check all the others to see their causal effects now, and they can come and suggest you a specific value, but wait, with a specific probability. And then if that probability is high, I can say, yes, trust this thing. So this is why we say here, we estimate the missing value using some the related neighbor. Here, neighbors here, I would say graph nodes, neighbors in a graph. Okay. If we now start mapping this thing into our CRM world, this can be country, this can be company, time, material, and product. So the graph now, we can, what we can represent here, of course, are now connected through shared metadata oral relationships. This thing can change over time, right? Other thing. So with this specific recursive graph convolutional neural network, correct? We pass information separately through different relationships along the edges that we have, and we learn which is matter most. So again, here we talk about a typical for us machine learning problem, and we are going to have trained data and test data later on. And the model between, which is going to come, has this structure inside. So the output for us, do not forget the code, with some imputation flags, and do not forget the indication here, right? Problem is simple. Problem is very simple. The more the data, the better result. And the uncertainty here will get lower if I have more data. Nice. I think architecture of the model, we for the RGCN block. And of course, to avoid overfitting, we also have a layer here with Monte Carlo techniques. Carlo, many repetitions. Drop out, so we keep one out if you like here. Why? Because we don't want the system that will overlearn from the data and will say that, okay, I found all the values with a zero uncertainty, so 100% probability. No. And then you continue gaze that we have here, which is in fact a decision maker here based on the inputs of those feature layers that they come as a graph. And then we start with the weighted aggregation, we linearize then the output, and then we have at the end the imputed production. Concept here is each annual record becomes a graph node over here before into the main block. The edges records, they share country, as we said, company, product, material here. This is the input, and then The model now comes and estimates the values from the related records, and of course, the output, as we said, is a new value which wasn't exist before there. So this helps. Why? Because we do not treat rows as independent. So actually now I can hear whispers from the nearby talks, right? Who are in fact neighbors and they can help me. Imagine that we are, I don't know, in a concert and we lost something, and then the two guys close to me, they know what happened, so I can hear them. This happened. Okay, now I can use it. Okay, I know it. You know, the temporal and the structural, sorry, context, and this is now better suited when missingness is high or uneven there. So here we talk about large gaps on the data sets, on the time series, not something simple. If it was something simple and dense data, I could easily use a mice-driven approach or KNN. Nice. So now, if one value is missing, the records can provide the context. So we have here a specific example. It's the time that you will start to show. Okay. So then this. There's more. Okay. Now in live coding, Stelina is going to show you a specific example where we start with a missing value that we have the whatever company product X and the specific year. So we are going to have some useful neighbors, same company in the nearby year, same product in the other companies, same country, same year. Of course, related reporting. Do not forget our goal here, which is the certainty. So we are going to show this with a code, with a live code example. So I give it here as an example. Yes. Yes, yes. Okay. Meaning that country A will the same, and then the missing that we are going to feed over there. So in fact, we stored here the observed value column, the final value column, the flag, because we need the flag, this model, the method that we underneath, where in this case is a specific neural network, and confidence indicator that we have. Okay, and then at the end, we might have a set of different cross layers for consistency and the mass balance access, which is in the beginning. So here we have the validation. Why? Because we want to compare related supply chain and after, let's say, values that are used for the modeling. So we have the mining output. So here we have the upstream material availability. And then we have the next layer, which is the refining material, manufacturing, that we have the demand signal and downstream, and of course the flags which are here not lit. And we have the example checks, refining, refining to mining ratio, and then some issues, flag values that we can have there. Interpretation, where we can have deviations that can indicate missing rows, like we saw before, wrong units or report artifacts, and then of course, last but not least, the model that we are going to use by here, because we want to keep value and pass a quality flag through the downstream. To the last step before the actual machine learning, engineering, and that can be temporal driven features, right? So some values, some rolling means, some grow rates, and then on the other hand, we can have simple capacity, quota, project. Then we also need to check the market and the flow over there. So trade flows, sales volume, inventory, and of course the quality. So the source scores, the imputation flag, as we saw before, the risk flag. And all this feature engineering should keep a certain interpretability here. So that the model input should still mean something physical to us. So with this, I think we conclude. So in the here, this set can be a certain guideline for features that you can use. And remember from the beginning, our goal is not only to clean the actually create trustworthy and robust inputs for later forecasting here, so to predict the future or for some decisions, if you like, or for some anomaly detectors. From the raw CRM records, all the things that we show, we come and see what we can, some tools that we have in our hands in terms of pre-processing, and then what we deliver, ready, artifact-free, let's say, data with no, if possible, missing values, with no outlier, forecasting which will come. I think this is it, at least from my side. I would like to thank. Let's keep questions in a hold because Stelina is going to continue. And we come at the end with questions. Ναι, κλείσε την τέτοια.
Hello, everyone. Can you hear me? I think yes. So now I'm going to present some code, basically. For the tutorial, we used our own data set from the rare earth elements, the mining one. I have already done a CSV out of the Excel of it. The purpose here, though, is not to build the complete scientific pipeline Marius presented, but just to understand some pre-processing decisions that we made. So the pipeline is the same. From the raw data, we go to the cleaning, validation, transformation, canonicalization, imputation, and feature engineering. Then finally, we get our ML-ready data set. So here I think we're mounted, but yes. So to start, we're going to import now our data set and to see its structure. So here we have the data set with the shape of the 796T and the 13 columns. So each column has a country, provenance, company, as we say, data granularity, input material and output material, the data type of what is it showing after, the production and the year. So we can move on to some light cleaning. First, we make a copy actually of our data so we do not ruin it. Then we drop some obvious duplicates that there are there. Also, we do not need these columns, so we do not get it here. And then we print the rows now that are remained. that are only 709 after the duplicates have dropped. We can continue to some light also validation. Here, this will tell us what basically needs more attention. So we're going to see if some production, which is our target here, is missing. And what years do we have? Because the year ranges from 2010, as we see here, to 2030, but we have data only until 2024, so the rest are future, and we do not see them as missing values because they are future values. Here, the unit is the same in all of our data, is tone of REE equivalent. So we do not also have any negative production. Another important for us issue is granularity, as we see. The file here, this data set contains not only country level data, but country level statistics, which is a little different. Cumulative of all plants in a country, and specific granularity for specific companies and countries. So here we're going to just keep the country level and the country level statistic, but for another purpose, we could keep the specific or the cumulative. We go on now to the transformation we make. Here we have to make the values comparable and separate according to their role. So a country with a production and a year. They are already in the same unit, as we said. And we have also to keep aside the future years with the historical one. So when we do that, the historical one are only 505 rows, and the feature that we kept aside are the rest. So before doing anything, we have to be sure that the countries have a name that it's canonicalized. So, for example, United or Myanmar can be Myanmar Prev Burma. It has to only be Myanmar, or United States of America has only have to be United States of America or USA. One of these, not both. So here we canonicalize the countries. So United States of America becomes USA, Russian Federation becomes just Russia. This is for our convenience later on when we're going to use the data set, basically. After this, we make two tables. One with country level statistic granularity and one with country level granularity. This is just because when we do not have a production from the country level statistics, we can go back to country level and take from there the production. This is mainly because sometimes there are human mistakes and they do not put the production correctly there. So here also we can see on these two tables how many are overlapping records. So we see that the overlaps are 30. We create a new panel so we can see the overlapping layers. Here we have also the observed and the missing from the overlapping layers that we did before. we see that the missing records here are 105, so a lot in this case. You can see here that Canada has some missing, Burundi has a lot of missings, Greenland too, Madagascar too, but we also have some complete time series like Malaysia, Russia, I think Australia too. And then we can go on quickly to some first missing data handling or the imputation in our case. Here we have to see the coverage of the historical values for each country. And with this code, we make a data frame here, and we see for each country the observed values that we have. So, for example, Canada here has from 2010 to 2024 two values, and the rest of them are missing. Or USA, for example, it has all the values there. We continue now with some of the imputation methods we mentioned at the presentation earlier. The easiest imputation methods to do are median and linear interpolation, for example. As we said, this is for the small gaps. So it works actually. If you do a linear and a median interpolation, we do not have missings after that. But in our case, it's not the best scenario because when we went and validate those data, the production, for example, got some values that they were not so accurate, and the testing we did. So before we will also examine KNN and mice imputation here, but before we do that, we always in these two methods you have to standardize the values for each country. This, as we say, is necessary because the production level they have different missings. Without scaling, a large producer could dominate, for example, the calculations simply because its number are larger. We see that especially in the USA, which has huge amounts of productions there. So we have to standardize this production here. Then we go on to KNN, which in our case, from scikit-learn, we just get the KNN imputer. We choose the neighbors to be 3. We can also choose 5, but 3 and 5 are the most common. So we look at the 3 nearest neighbor to fill the missing values. Then we make the data frame out of it, and we scale it back from the standardization we did to the original values. And of course, clip the negative. And we see that, yes, also KNN can fill these gaps, all the gaps and the big gaps. But as I said, in the testing and validation we did, it was not enough. So we go on to mice. If anyone doesn't know, mice is an iterative method. It estimates one country from another country series and repeats this process for several times. That's why it's iterative. So again, we take the iterative imputer from scikit-learn, and here we put a tolerance of 0.2. So this is a stopping criteria for our iterative imputer, so it knows when it's going to stop. And we keep a random state the same all the time, so it gives us the same results. So here then we collect all the methods we did before in one dictionary, and we're going to see how each of them has done the filling above. So we can select with a random state one random country here. You see, if you change this value, and here we can see all the imputation methods, how they are reacting to the missingness. For example, here in Burundi was easier because it has only edges, not in between. So in between, all the methods preferred the same. It was the same performation, but in the edges, the mice actually was a little crazier, we can say. The other three methods were more in the same direction. So we can now go on to the some example. We have to keep the linear interpolation, the easiest one, and here, as we said in the presentation, we have to also have an imputation flag. So our model later knows which value is imputed and which it's not imputed, it's observed. Here, for example, Australia has this, well, here, because we got the head, Australia has no imputed value, but if it had an imputed value, it would be true here. And we can go on now to the feature engineering, our last step. For feature engineering, you can do any feature you like, but in our case now, for this short tutorial, we used the production, which is our target also in the current year, and it's on our main input signal. Lag, which is the production of the previous year, the rolling mean, which is the average production over the previous, how many years you're going to define that. I put 3 here. This is the standard one. And the flag that we did before, was imputed. So the model can know if the value it's looking at, it's imputed or it's the observed, as we said. So we put here our features, the lag one by shifting by 1 the historical values, the rolling mean by the average production of the previous 3 years, and the target next year with the shift of the next value. So in the end, we can see that our ML-ready dataset should look something like this, should only have our features that the model can understand. Also country, it cannot understand the country or was imputed. They have to later be not non-categorical, but this is for ML step. So here we can see that our ML-ready dataset has only 7 columns now. It has the important ones, the year, the country, the production in what unit, tones in REE equivalent in our case, and then the 4 features we mentioned. So in our case, though, in work package 4, we did the imputation by a graph, as mentioned by Marius before. Why a graph, though? Because, as I said, this methods that we saw use a time patterns or a similarities in a flat table only. But our data, the critical raw material data, they also have a relationship between them. So the companies may be from the same country, for example, or they may have the same materials. So when you do an imputation, you have to take that into account too. So a graph represents those relationship, and specifically our graph can use more than context when it fills the values, the missing values. So that was all from me, and here are some references for this tutorial.
So I think we have 4 minutes for questions. Okay, we're a bit of time, but we'll go up to 11:15. Just stay. Are there any questions from the audience?
If I may ask about the imputation, we have seen you presented some methods that you said it gives us the probability, and if it's high probability, we keep it and all. Other stochastic methods have been considered in this regard, and could you tell us a couple of words about them in the context of this presentation and what we're trying to do?
Do you hear? Yes. So you said that other stochastic methods do the same? Because we were talking about relationships specifically in the dataset. So when the dataset has a multi-relational combination there, where its record, you have to take into account the whole similar records, so you can do a proper imputation. We basically followed this approach because all the simple imputation methods we used, we did the testing, the evaluation after it. We seen the distributions that changed with the observed versus the imputed data set. And we ran over a really interesting paper which has done the RGCN model. It's not our model. So we took that, and the imputation values were really good then. The distribution had remained almost the same, but it was really close. And my and all the metrics we used for evaluation were really good regarding the other imputation methods. I'm not sure I understand.
Thank you very much.
In fact, there indeed you might have some optimization-driven approaches like following gradient descent or something else, or Monte Carlo. You may also go and synthesize some of the data, do some surrogate data analysis, and then to decide from pure probability. So you create a normal distribution, then you might have the null hypothesis, and then you can decide from that one. There are several over there. So the goal here, as Stelina also says, was to bring something novel and something like this. Yeah.
Yes.
Perfect. Fantastic. Other questions?
Thank you.
John?
So thank you for the nice presentation. You mentioned that after the imputation, you look at the data to decide if it's good or not.
Yes.
How do you decide if it's good or not?
Well, I can. Do you remember in our work package meetings where I put some metrics and the KD distributions there? This was the decision. I have also, we have uploaded with Susan a paper in work package 4, which says these two methods. So you have to look at the distribution and at the two matrix, the Winchester distance, something like this is the name, and JSD, those two metrics.
Thank you.
You're welcome.
If no more questions, I think we can have a 15 minutes break, and then we can continue with the next talk. So online people just hold for 15 minutes. Thank you.
Attention. I think we are ready to start with the next presentation of today's workshop, where our great colleague and TUC researcher Giorgos Livanos will talk to us about machine and deep learning for rare earth forecasting. George, the floor is yours.
Okay, thank you. Can you hear me? Okay, hello everyone. This is the talk 2 for the workshop on data processing and AI-driven REE forecasting. This is the outline. We'll have a short introduction, a few a few words about the key theoretical aspects. We'll present the tools and data sets. We'll talk about the open pit mining sites monitoring, the integrated solution that is being developed under the MaaSiveTwin project, and the conclusions. Why do we need REE forecasting? Because rare earth elements are small volume materials with system level impacts in magnets and in many technologies. The supply is risky driven by multiple factors, and classical forecasting techniques often lag because many variables are reported late, aggregated nationally or hidden in company data. We have also some indications from the EU that the demand will increase by a factor of 6, and we have the EU 2030 benchmarks about 10% of extraction, 40% of processing, and 25% of recycling to be done annually in consumption. So how can satellite imaging contribute to this? We'll see the REE forecasting on the perspective of image analysis, and specifically satellite image analysis. So how can satellites help? REE markets are affected by physical activity at mines, processing sites, transport corridors, and export nodes. Many official indicators are delayed, so satellite imagery adds near real-time spatial evidence, and the objective is not just see REEs directly, but monitor observable proxies and link them to supply capacity and disruption risk. So we have two key parameters. We have to make a proxy, which is an estimation of a hidden supply variable, and consider this in the perspective of time. The indicative illustration of how we frame this problem. The supply chain is spatial, temporal, and observable, so we have to deal with many stages: extraction, processing, products, transport, and demand. So in this pipeline, EO adds a missing layer, which is physical activity signals before official statistics arrive. So extracting features from satellite images can help us forecast the entire supply chain. We have also some evidence from the USGS that enables this need for forecasting of rare materials. So how we frame the problem? We consider the Earth observation as a leading indicator layer, where we consider different imaging modalities. We derive geospatial features, we feed the data in forecasting models, and then we have signal types extracted from imagery that are related to different actions, activity intensity, spatial expansion, deformation, and environmental pressure. we have to be careful in the forecasting design, because we don't want just to see the ore in the ground, but we need to model and monitor the supply changed state. This modeling can be site level, but the decision question is usually regional or supply chain level. This gets out of the local level. So the series is that we have traditional target variables. We derive predictor variables via the Earth observation approaches, and we feed the models that produce the forecast outputs that can be related to near-term supply risk, production trends, disruption probability, flag indications, or scenario signals. The overall, the simplified architecture consists of the data retrieval, which is in our case based on Sentinel-1 and Sentinel-2 images, potentially from other external content. We perform the pre-processing, as Marius and Stelina showed. We create the feature store. We apply the ML-DL forecast models, and then we give the outputs to the decision products. Three key notifications. We have to keep EO features traceable. We fuse EO data with non-EO covariates only after temporal alignment. And we have to design for update cycles to make this procedure repeatable. So how this theoretical or scientific or research framework can be translated to a real product in use. We have 5 steps: acquire the data, process data, extract features, forecast, and then provide the alerts in terms of visualization tools such as maps, risk scores, reports, or other indices. Let's see a few theoretical things about satellite imagery. It's a service that is already been accelerating. There is a huge interest in satellite imagery, and there have been developed many tools that help us understand better this kind of data. Of course, there are many limitations for optical satellite images. The biggest barrier is that the atmosphere can insert noise in our data. Yet, optical images are not the only way to visualize Earth surface. We have different imaging modalities, and combining them and applying clever pre-processing methods can help us enhance the feature quality. So we have to consider satellite image as not a photograph. It's a very complicated framework. It's a combination of metadata, data, raw data that are hidden underneath. Thus, the processing and pre-processing algorithms have to search deep in these frameworks. And the most important is that depending on the application, we choose a proper imaging modality. The advantages are that we can increase coverage areas compared to simple imaging equipment. The transmission is independent of the distance. We can have higher bandwidth and multiple wavelengths available, yet launching satellite into orbit is costly. On-demand data are not free or not available, and we have to deal with a huge amount of data. Our basic tool is Copernicus Data Space Ecosystem. It's a series of Sentinel missions. We have focused on Sentinel-1 and Sentinel-2. Sentinel-1 gives us the ability to track and monitor the activity on the surface, and Sentinel-2 enables us to detect the objects of interest or the areas of interest. And combining these two modalities, we can have an actionable framework that can fit the forecasting model. Let's focus on Sentinel-1 imaging modality. What can it tell us? It can tell us about the surface substance, the roughness. We can identify the ground, the materials underneath. We can have interferometric phase, which means that we can monitor the deformation of the ground. We can have coherence, and this can feed us with a forecasting value about the evolution of ground degradation that takes place. Sentinel-2 modality, on the other hand, can tell us more about the visible or the non-visible characteristics of the area, which means that we can identify different structures on the surface, mining sites, rivers, land, lakes. Different bands can be resampled and can fit already stacks. And for open pit monitoring, the output can be a probability map or a complicated visualization tool that enables us to extract information and give the instant visual information about the surface to be monitored. Okay, better now? Okay, now better. Okay. So how we proceed from the Copernicus data space environment to the ML-based satellite demand analysis. We search the database for proper imaging modalities. We download the .safe products. We identify the bands of interest. We make the preprocessing and quality assessment on the data, and then we provide we extract the ML-ready features as already Marius and Stelina presented. So the different imaging modalities give us a different kind of information. So what kind of features can we extract? First of all, we can extract footprint features, numerical assessments on mining area, expansion rate, new activity identified. Spectral features such as spectral indices that differentiate its material on the ground, radar features which are directly related to mining activity, spatial aggregation, uncertainty features, and temporal features. This is very important so as to have a time series monitoring of a specific mining site. The modeling logic is that we extract features from the satellite images. We create the feature store of interest. We make the model training, perform the forecast and the scenario, and then we have the final decision products. What models can we use? Classification models, segmentation models, time series models to estimate trends and predict near-term changes, or hybrid models that combine both activities. And the tools are classified in 4 main categories: the data access, preprocessing, insight analysis, and visualization, mostly using GIS tools. Let's focus a little bit on the Sentinel-1 imaging modality.
what this the tool we developed can extract. Relative displacement, deformation trends, hotspots and instability zones, change points after mining activity, and confidence flags from coherence and temporal consistency. The output is sort of a heat map which can interpret the colors to the ground deformation evolution. Translating this to a feature layer, we create the so-called interferograms. They are the maps shown in the previous picture. We have the time series deformation, spatial aggregation, anomaly detection, and finally we have the forecast figures. Towards this, we can have three kinds of metrics: site level metrics, temporal metrics, and risk metrics, which are most related to the supply chain modeling. On the other hand, we have the Sentinel-2 imaging modality, which are mostly related to what we see as on the surface. So we can detect the mining area, we can isolate the borders, we can have spectral preprocessing and tiling and identify the different materials present on the area. We can then have a post-processing, perform a post-processing and incorporate the output in GIS-ready pipelines. And then we can also have a quality control and human review once needed. Constructing the Sentinel-2 feature layer, we can combine geometry, spectral surface chains, activity proxies, and GIS outputs. If we combine this, the satellite data with on-site close-up monitoring, such as using drones or other equipment from civil engineers, we can have a better and a more accurate estimation of the 3D geometry of the mining site. So how we build the model layer? We can combine multi-resolution spatial features, lag-aware training design, perhaps uncertainty-aware outputs, and we can use or combine specifically one or more models in the categories of tree models, temporal models, or geospatial deep learning models, and then feed the forecast ensemble. The key step here is to keep the temporal alignment, which is the hidden challenge, because we have to keep the five key steps of data acquisition, preprocessing, feature update, reported target, and forecast horizon, and this can be repeatedly done in a long time rates. The key roles are use only images available before the forecast issue date, aggregate features only physically meaningful windows, means we have to have certain timestamps. We can use, it's better to use test lead lag relationships rather than assuming immediate effects. The evolution in the surface goes very slowly, and avoid special leakage in this pipeline. This table summarizes and gives some examples of how we go from feature space to the forecast use. Of course, it's not enough to build the model, we have to evaluate it. So we have different validation frameworks, such as remote sensing validation, forecast validation, and decision validation. And validate the distinct steps of this framework The important thing is that accuracy alone is not enough. The feature must be timely, stable, and decision relevant. It's not. We don't just want to create features or metrics without knowing how to interpret them. The innovation to all this framework is that we can proceed from images to supply intelligence and extend the site level information to the entire supply chain, integrate radar deformation, move beyond static mineral potential maps, and create dynamic operational indicators, support transparent forecasting with physical interpretable AO-derived variables, and combine different technologies. So we go from data space, visualization space, and forecasting ready data, features and metadata. Of course, this modeling has to be in a very responsible manner. The main limitations are that atmosphere and especially clouds create noise. Models need quality data to be used as inputs and need quality assessment on the data, and we have also operational safeguards such as uncertainty flags, human in the loop, quality control, site level audit details, and etc. The outcome is that forecasting should support the prioritization and not replace the expert opinion. Proceeding to the tools to access data, we have three main categories: the freely available, the research projects selected, and the commercially available, which of course have the cost. We have focused on the first category. Some examples of with links for data repositories. So let's focus on the Copernicus data space ecosystem and forecasting. We proceed from human exploration to automation. This repository provides us with data, tools, pre-processing tools, and that are available online. And especially for REE forecasting, Copernicus data space helps build a consistent evidence layer around mines, transport corridors, and the regions. And we can perform the exploratory work through a browser and repeatedly searching for the data based on the site of interest. These are the main data layers for mining and REE supply chain monitoring. We have the Sentinel-2 and 1 repositories. We can also have information about the digital elevation maps, which are related to topography, and we can also have external context data. Copernicus data space also provides us with different APIs and services, so as to build our own applications. We have selected some, and we will present the implementation later. The overall pipeline is that we find products, download files, stream or process data, analyze in cloud or locally via our algorithms, and we export this data to third-party applications. The rule of thumb is that we use browser tools for exploration, the APIs for acquisition, and the cloud services for scalable process. The latest is a newly inserted service, which we intend to use intensively. The operational workflow for REE forecasting, we search the area of interest, the dates of interest, we download data, we pre-process data, we extract features, fuse data, and finally forecast and monitor. What can we have as an output? Site level and regional indicators, such as disturbed area extent, expansion rate, deformation hotspot, etc. The core message is that Copernicus data space makes satellite-derived features reproducible. This is an example of how we use the browser to download Sentinel-2 data. It's and the ins are the optical, let's say, the RGB, let's say, information, where we have different fields to select. And this is the Sentinel-1 modality and the specific fields. So going into practice, why is monitoring of open pit mining sites from space such important? Because surface leaves visible physical footprints. These footprints change before many official production or supply chain indicators are published. So satellite monitoring can turn repeated observations into early signals for critical supply chain modeling. And the core idea is to use Earth observation data to measure mining activity consistently, repeatedly, and at a scale. The challenges are many. First of all, remote sensing data are complex. We have to dig very deep so as to understand all the information. We speak about 7 to 8 gigabytes per mission. So when required to access more time points, the volume of data is then very huge. We have the geospatial complexity and we have the operational complexity also. So for the methodology point of view, what is the contribution or the foundation, the scientific foundation? Is to perform pixel by pixel mine detection. There are lots of tools. We have, we'll present the fusion of these two tools in our case. Of course, we have listed some very indicative models to start with. And on the other hand, apart from identifying the area of interest, we can proceed to the next level, which is to monitor the ground evaluation on this specific area of interest. This is based on the physics or the theory on how wavelengths interact with surface. I don't want to make it very theoretical. The key point is that we can, by recording the reflectance of this of the light, we can model the properties of the surface. We have two types of information in this modality. We have amplitude, which is related to how strong is the return signal, and the phase, which means how changes in satellite take place and evolve upon time. Combining these two images, we can have the ground degradation evolution monitoring. This is done using constructing the so-called interferogram. It's a visual tool that highlights the spots of within the area of interest that change upon time. The important thing is that we need two images taken at intervals in different time. We cannot reconstruct this map from one image only. These are the steps of how to construct the interferogram. and how we move from visual from qualitative information to quantitative information and measure the degradation in terms of centimeters, meters, etc. So we now will go to the integrated solution we developed in this project. It consists of three stages: observe, extract, and forecast. So we have developed so far three tools. The one is the API to connect to the Copernicus data space. So we have made a simplified graphical user interface to retrieve the data. We have a GUI-based automated open pit mining site detection, which makes the segmentation of the mining site. And once we isolate this area, we can move to the complicated step of ground degradation evolution. But since we have isolated the area of interest, we don't need to process the entire image capture in the .safe image data. Regarding the image segmentation to extract the mining site areas, this is the simplified workflow. The important thing is that we have used a pre-trained model. We applied it on our own data. We'll also, as a next step, we'll retrain the model with the specific data for mining sites. The important thing is that we have simplified this procedure via a user graphical interface. So the user does not have to write commands or make complicated processing or perform processing algorithms to make to take the output. It's they are all integrated in one graphical interface. This is the overall framework. So we move from data collection, data preparation, which we use the annotated data of the authors. We perform a segment model for the segmentation. The key idea here is that we split the images into tiles, into very small images. Then we perform the segmentation there, and then we combine all these small tiles into the overlaid image at final. This is the GUI. It has 6 key tabs. Each tab makes a specific thing, and we have a sequence of steps from splitting the image in tiles, pre-processing, make the inference so as to make the segmentation, perform the segmentation, the quality control, stitching image, and overlaying the image so as to show the output in a visual tool. These are the details for the two core models here. The one is the architecture that the deep learning model that makes the segmentation, and the other is the one that recognizes the areas of interest and makes the overlay and builds the big image from the tiles. This is the end-to-end workflow. The important thing here is that we use different bands, and the segmentation is performed in 8 key ones. So we don't use only one channel for performing the segmentation. And the pipeline is the identification of area of interest, the selection of proper bands, the inference, the mosaicing to identify the specific tiles, and the procedure to integrate all the small outputs into the final image. These are the steps in more detail. And this is the final result. We begin from the raw data. We extract the masks, which are the potential mining site candidates. We filter these areas based on the morphology and their properties. And finally, we overlay, we build the overlaid image, which is the final output that the mining site has been identified in terms of bounding box. What's the contribution of this? First of all, we have a graphical user interface instead of prompting different commands. We can have a preview and feedback of the result or the intermediate steps. We have the workflow safety because we have organized data into separate folders. We have the ability to integrate with third-party applications such as the GIS workflows. We can also increase data quality, and the limitation is that depending on the specifications of the hardware, we can delay or make this procedure faster because it's a time-consuming procedure. Regarding the segmentation workflow, the added value is that non-programmers or the beginners can use this workflow without going deeper in theory. The outputs are geo-referenced, so they can be used in other applications. And these open pit footprints can become reusable for supply chain forecasting, as it is done in Work Package 4 in the MaaSiveTwin projects. The direct next steps is to further validate the set for target regions, perform some ablation tests, retrain the model with our own data, and the future improvements lie in the 5 following directions: better trained data, multi-sensor fusion, time-aware forecasting, uncertainty in validation, and finally, integrating supply chain models. This was the first part. The second part of our pipeline. The first is the data retrieval. The second is the mining site segmentation. The third is this one, which transforms the visual information into quantitative assessments on mining activity. This is the most important thing because the features and the metrics of this pipeline will feed the forecasting models for the entire supply chain. This framework can tell us about the volume of can give us a proxy of the volume of data excavated. Then the next step of another task will be to monitor the transfer of this raw material to the processing units, and this chain is filled with the next step. So this is the key and the first initial step for monitoring the raw materials from the source. The pipeline consists of 12 steps. The first is to make the proper configuration for the application, acquire the data, handle the orbit or filter depending on the specifications of the satellite mission, perform some pre-processing. The key task is to co-register the two images or the multiple images if we go for time series monitoring, extract the them the digital elevation map, unwrap the face so as to extract the temporal information of the ground degradation, and then integrate this information using at least 3 scenes so as to have a time series assessment on how the mining activity has evolved from the starting point to the end point of our study. We export the data, the metadata, and then we visualize the output. Concluding, Earth observation can provide earlier spatially explicit indicators for critical material supply forecasting. The Sentinel-1 and Sentinel-2 imaging modalities are complementary. As you saw, the Sentinel-2 identifies the area of region, and then the Sentinel-1 data processing focuses on the specific area of interest and saves many processing time instead of searching in a blind manner. The next methodological step is a validated feature store linked to production, and as the project evolves, to integrate this output to the next stages of the forecasting pipeline, as Marius and Stelina showed. And the next practical step is pilot monitoring on selected pit mining sites. Regions, we have a database of around 50 mining sites with GPS coordinates, and this will be the initial validation cases. The take-home messages, Sentinel-1 and Sentinel-2 provide complementary evidence for monitoring mining activity. Deep learning approaches can convert raw satellite imagery into geospatial products that can be understandable. The GUI-based frameworks we have developed make this process automated and more easy to use even for beginners, and which is very critical if we think of having the demonstrator as a open source or a commercial product too. And for raw elements forecasting, satellite outputs are best used as proxy values so as to have an initial estimate. Thank you very much. And you have questions?
Questions? Are there any?
Thank you very much. Really, really cool what you're doing there, and very inspiring. I just have one question regarding the coverage of this Sentinel image. Is this for all parts of the world? Maybe I missed this. Is this global? And if so, do you observe there any differences in the quality, how well these the different areas of the world are covered, or is it basically a great solution for all parts of the world?
Other questions? I may have one. Potentially, I might have many. As to the tool, so now we talk about, let's say, one of the first steps of the project. So in real time, one can. So now the system, let's say, it's connected to the Sentinel database, right? And you can have images from hyperspectral and the normal ones, the C-band, I think, the first one. Okay. Exactly, the optical one, the word that I missed. And first of all, you have there a specific segmentation method, which is pre-trained, right? So there is, for example, no fine-tuning underneath of this method. There is no new training of this model, so you just use it. It's pre-trained. To fine-tune based on how many images? Let's say some thousand. To scratch, and then the more data that we have from the Sentinel, or this is fixed. So we have a database which will no longer have new images, so we have 100,000 of images, and that's it. Correct? Okay. In the class of interest, let's say. Yes, okay. Okay. And let's say as a dummy user, so we have this model that has a knowledge over there. So in from a visualization perspective, I open an image, I select the region that I like, I press a button, I do the segmentation. Okay, yeah. Mm-hmm. Okay. Uh-huh. Okay. Okay. One, yeah. And all these you can have them for a specific timestamp, right? Or for as a time series. Okay, but this is yes. Okay. And the last question, let's say, yeah, the first version, let's say, down version, yeah. Yeah. One more, let's say, I didn't understood well. So from the Sentinel, the images that we get are already geolocalized. Perfect. Because we know this is like a hard task to have the geolocalization, so this is already good. Yeah. Okay. Yeah, that's what I mean. Yeah. 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 Yeah, this is the very, very important. And one very last, just to connect with the, we have time, yes. Just to connect it with the previous one, and I may probably miss it here. So you also do a kind of pre-processing in the images, right? Okay. What we get from the Sentinel is something raw again here, or okay. Like we said before, certain, let's say, pre-processing steps again, not for a 1D at time series, but now for a 2D time series here, which is even more complicated, you can say. Yeah, that's perfect. Yeah. Yeah, it takes time. And George, one more question, sorry. Did you face any issues? So I want, let's say, to segment and to get the title of a specific mine area. Was there any problem there? So there was any areas that were restricted, like that we have with, I don't know, with the US bases that you cannot, that they are blurred? They are still open. Yeah, this is something that, yeah. So at the end of the day, this will be an open source tool together with open source data that someone can really use, can validate, can come with comments, suggestions, and just to contribute. Yes, of course, of course. In terms of the project, some commercial and very complicated activities and processes underneath will be closed, for example. Yeah. Okay. Other questions? Cool, cool. I think we can just conclude the first part of the workshop. I may have to apologize a bit, it was a bit heavy as the first part. So we saw a few things about signal pre-processing in the raw materials, image pre-processing and segmentation. So at least we learn a bit how to extract features, and we haven't seen how to do the forecasting. And this is, of course, part of another workshop of this project. So stay tuned, I have to say. I hope that you learned something, and then we'll stop here for a long break, let's say for a long lunch break, until the next two talks, which will start at 2 o'clock Greek time. And there we'll see things about really raw materials, and then something interesting for all of you, digital twins and digital shadows, in fact. So thank you very much, and see you in 1.5 hours.
Yes, sir.